Okay, in the last video, we talked about a vending machine being a function. Right now, let's go ahead and get some official definitions, which we didn't do, and then we'll go on and talk about what we can do with the function after that. Remember, this is the heart of algebra, so we got to get all of these pieces arranged. So we did say in the last video that a relation was a pattern. So here's a more of official definition. It's a set of ordered pairs. Remember, ordered pairs kind of come in a pattern. An ordered pair, then, just to remind you, is a point represented by an x-coordinate and a y-coordinate. We know them as inputs right now, buttons, and outputs, which is snacks, but more familiar with them as x and y from previous classes. Again, we got to know those relationships there. A function then, and this is kind of what we were hinting at in the last video, is a relation that assigns exactly one output, one snack, to each button combination that goes into the vending machine, or x-coordinate. Okay, and then later on we'll use this definition, but right now today we won't, which is a vertical line test. We're going to use the vertical line test. It says that if any line passes through more than one point of a graph, then the relation is not a function. So we just brought up the idea of graphing. Well, our vending machine didn't really have all of the information we need to graph. So I'm going to pull up another vending machine here that has some information and can produce us some ordered pairs so we can graph, and then we can kind of see what parts of the function there are. Real quick before we do that though, are all relations functions? No, not from the definitions and everything that we've seen. Are all functions relations? Yes. So how do we know that? It says all relations are not functions because what we find is there's going to be bad vending machines, things that aren't going to put out what we expect them to put out. You haven't seen that yet, but we will. And then are all functions relations? Yeah, we did say that. We said that every function has the special part. If we put an input in, an output comes out. And that will always be true since relations are ordered pairs. All right. So back to our vending machine here. Here's our new vending machine. And the reason that we want this new vending machine is it's got some dollar amounts in there. And dollar amounts will allow us to create some ordered pairs or some coordinate points, which we've done in this table here. So take a second, make sure that you copy these down. So all I did was take in the first space of the vending machine, write that down as my number or my input because it's a button combination, right? So I pressed 1 and I get pretzels. But this time, instead of worrying about getting pretzels, we're going to see what price comes out and see if we'll just see what's there. We're going to look for a relationship. So I get $1.10 out. If I press 2, 2 goes here as my input. My output then is going to cost me $1. If I press 3, 3 goes here. That's my input. My output then costs me $1.50 according to this one. So fill out that chart the rest of the way. And then what I want you to do is pause the video, and then you're going to graph down below. And I want you to go ahead and practice your graphing because we haven't done that yet in class. So pause the video, graph these coordinate points, and then we'll check them in just a second. All right. So you've had a second to do that. Let's go ahead and scroll down here. Again, what can we do with relations and functions? Or more specifically, we're going to start to focus on functions now. We just saw that we could take something of a vending machine that we could put inputs in and get outputs out, and we could get a table of values. For every button combination or every input, we had a price that came out for that particular snack. So for every input, there's an output. If there's a pattern there, we would be able to see it we could see it in the values, but a better way to possibly see the way that this pattern may come out is by putting it into a graph. So if we graphed all of the points and we could look at it, we could see here, this is the pattern of this graph. Well, this particular one doesn't, but it was a nice way to get a vending machine. But what I'd like to call to your attention is that there's 4 parts to a function that we just talked about. You might not have seen one of them, but can you come up with 4? So take a second. Pause the video. What 4 parts of a function did we just talk about? All right, so hopefully you came up with this. This is what you should have found. You were just asked to find what 4 parts of a function there were. So what we'll see is that the function can be broken up into 4 main parts, that being these 4 here, okay? Which is a scenario, which means the problem. So this would be the part of the actual vending machine, right? That there's reality to it. So it's like a real world problem, a story problem, if you will, the context of what the problem is explaining. Because when we do math, even though in math class we don't do it all the time, math's purpose is to explain something that's in reality. So that always is a huge portion of what we do. And you did see the table. I'm guessing most of you came up with the table because we saw that one there. And then I did ask you to graph, so hopefully you came up with the graph there. And then finally, the one that I said that you may have seen or done, or maybe you came up with, is that there may be an equation, or better yet, let's call this a function rule. Okay, a function rule then is what explains the points kind of going into the table, what it makes, what is creating this pattern in the function. So let's take a look at another example here. Again, let's just reiterate. There's just 4 different ways to say the exact same thing. And let's highlight that now. So here is the reality of the problem, or the context, or the story problem, if you will. It says Mrs. I borrowed this. It should say Mr. Mr. Hallam's class has 10 students on the first day of school. Every day, 2 more students are added to his class. How many students will be in his class after 2 weeks? So that's the scenario. That sounds like something we can model, right, with a function. So we're going to put values, right? A function then is putting values in, having things come out, which creates ordered pairs. And ordered pairs we can now graph over here. So this helps us create ordered pairs. The ordered pairs allow us to graph there. And then we can even make more sense of this by writing a function rule that kind of explains exactly what happens, which can also take us back to the table, and we can graph from it that you'll find out a little bit later. Okay, so this table here should represent what we see here. It says Mr. Hallam's class is 10 students on the first day. And if we go back to this table, we can see that there's days. There's exactly on the first day that there are 10 students. It says that 2 more will enter each day after. So on day 2, right, we've moved a day. We got 2 more students. Day 3, we've got 14 students. Day 4, we've got 16 students. So that generates a set of ordered pairs. Again, lots of information can come from that. We get specific locations. These are considered points. We can graph them. It gives us the ability to graph. They can be quick reference for pulling up, oh, what happens on day 10? Oh, he's got 28 students. It can be a quick reference. But more, it can also tell us how these outputs are moving. How are they changing as we look down or up the list? This one looks like they're changing by +2. It gives us an idea of what's going on. All of that information we pull from a table. So what does the scenario, the story problem give us? It lets us see, we can kind of see the pattern as we talk about it. Does there a sense to what's going on? Who, what, why, all the different parts of what's going on. But more importantly, it's how to use the given information. Because again, we don't do math just to do math. We do it to explain a situation. So we need to understand the situation by looking at the scenario, the story problem. Well, what's the graph good for then? The graph is great for actually visualizing what's on the table, right? Or visualizing what's happening in the scenario. What's the trend? Is it moving upwards as we move left to right? Is it moving downward? Is it increasing? Is it getting more steep as we go across? Or is it kind of at a constant rate? So it allows us to visualize what's happening in the scenario, what's happening with the specific coordinate points, and see what the pattern's doing. All right, can we even extend the pattern? Will it keep going? Does that make sense to do? Again, all of these are the exact same thing so far, right? And then the equation is another way to kind of look at the parts that are controlling the pattern, or the parts that are making these coordinate points. So what do I mean by that? The number of students in Mr. Hallam's class is controlled by 2 students times a day minus 1. But here's the +10. I know that was a strange way to say it. So here's the 10 students that start in Mr. Hallam's class. You should be able to see that. Here, this piece then is controlling how many students are coming into Mr. Hallam's class. Now, remember, he's got 10 students on day 1. So day 1 already exists. So to get this pattern to work, if I put 1 in here, right, 1 times 2 is, 1 times 1, let's plug it in actually. If I put 1 minus 1 in there, that turns to 0. And then 2 times 0 equals 0. That gives me the 10. So the reason that there's a minus 1 there is to make it work on the day 1. If we didn't have the minus 1 there, look what would happen. We'd have 2 times 1, because that would be day 1, times 2 students plus 10. We would get 12. It's actually kicking out what happens on day 12. You'll start to come familiar with this. Don't worry about the -1 for now. But the more important thing is this rule, if we change this piece to 3, meaning 3 students a day are added, then that changes what happens up here. So this is kind of the inner workings of the function rule. This is the specific values or points or integers in this case that we're looking at. This is a visualization, the graph is, and then this explains it so that we can make sense out of the whole thing. Okay? So those are the 4 main parts of a function rule. So what I'd like you to do now is pause the video and see if you can fill out this next page. and then I'll bring it back up and we can chit-chat about it and make sure that we're all together. Okay, so you're back. Hopefully you took a second to fill that in, and you've got something that looks similar to this. So it says Mrs. Champa, yeah, she's the one that made that, so this Mrs. Champa, we're doing good now. Mrs. Champa decided to order some pizza for her class. If the pizza costs $5, right, $5 to start, and each topping on there, each additional topping costs $1, how much will a pizza cost that has 7 toppings? Well, to start that, let's just say if I have 0 toppings on this pizza, it's going to cost me $5. If I add a topping, $6, $2, or 2 toppings, $7, 3 toppings, $8, and you would have filled out that table. Again, all of you could have done that. If you move down here, you would have started to graph these points. So these are coordinate points, right? These are inputs here. So my input would have been a 0 or an x coordinate, and my output would have been this y coordinate or 5, and you would have plugged those points in, meaning x coordinates go on the x-axis, or give you the location on the x-axis, so at 0, and then I would have went to 5 on the y-axis, making these points here. Okay, so you should add something that looks similar to that. You can tell, just to kind of throw a little bonus in, that this is increasing very consistently, or what we'll say is constant. Okay, so now we got a visualization of the pizza toppings and how much they'll cost. This then, and this might have been tricky for you, maybe you could get this, maybe you couldn't, but here's the function rule. Again, here's our y value. T represents our x, just to kind of give you context. Sometimes we change the variable's name. So we're saying that the pizza costs $5 and that every other topping costs $1 on top. So this will help us write the rule that explains what's going on. So if we plugged in a value up here, right, like 1, we should get 6 out of it. So what would that look like? We would say the pizza cost per topping of 1, right? We know should be 6. Here's our rule, 5 plus, and then there's the t, which we said is 1, minus 1, which makes 0. So we get 5 plus 0, or $5. So the function rule creates the table. So what does all this tie together? Kind of what we said. So here's your summary for the notes. We talked about what a function is. It can be understood as a vending machine, meaning that we have inputs, or the buttons that we put in, and outputs that come out. It's very specific that each button, or each button combination, goes to exactly 1 snack. Okay, exactly 1. Now, what is a function rule good for? Modeling real life. What are the parts of a function? We get the scenario or context, we get a table, we get a graph, and we get an equation or a function rule. This is what we're going to apply, these basic rules, to every function we're going to find all year this year. Okay? All right, so I think I've covered everything that you need to do. We've summarized, and now I'll see you in class for some problems.